Start by good morning.
Morning.
Couldn't touch your papers to grade this weekend. I got very sick after the Friday lecture and I'm still kind of trying to get out of it. So my throat is hurting. My nose was just like a loose faucet and beginning to develop some cough. Kind of assembled myself together and came to the lecture. So let's see how well it goes. Do you have any questions for me? I believe this Friday we're going to have a lecture, right? That's the fall break. So likely you won't see those graded paper until the following Monday, because I doubt that I'll be able to get them by then. What I have on the board here are the two curl equations, which are part of Maxwell's equations. And I just spelled them out in Cartesian coordinates, right? There's nothing unusual about that, because we're working in rectangular waveguides. Rectangular waveguides are being analyzed in Cartesian coordinates. So we need to get back to those, because what we've done, if you recall in the beginning, was to combine all four Maxwell's equations into the second order differential equation. And we solved the second order differential equation. We ended up with a few constants. And we know that we have to get back to the first order equations to be able to get all these constants spelled out. Out of the second order differential equations, which were what? We had del squared E is equal to, or minus omega squared mu epsilon E, which was Ex, Ey, Ez, Ex, Ey, Ez. And we had another one similar to that, which was del squared Hx, Hy, Hz was equal to minus omega squared mu epsilon Hx, Hy, Hz. In principle, you can think that you got 6 differential equations, each one is in one variable, so you can solve them, right? You can solve each one of those. You can get Ex, Ey, Ez, Hx, Hy, Hz, right? But each one of those will have its own unknowns, right? Like we did the EZE, and what did you find? We found sine m pi x over a, sine n pi y over d, and then we had EZ plus e to the minus j beta z. I'm forgetting the m and n here and the subscripts, but we know that they are there, plus EZ minus e to the plus j beta z, correct? We did that. So if you do this, you will have, again, more unknowns, more constants, more parameters, more parameters, more parameters, more parameters, more parameters, right? But all these parameters here, the Ex, Ey, Ez, Ez plus, Ez minus, all these constants that we have here are related to each other, right? They are interrelated by these relationships. When you differentiate those to bring it to a second order differential equation, you lose some of that information. So to get it back, you have to go back to these. So in order to get those interrelationships, you have to get back to those. Otherwise, you just have those with arbitrary constants and you cannot relate them to each other. In addition, obviously, to the boundary conditions. We use the boundary conditions to knock down some of the constants here, if you remember. This was Kx, this was Ky, and we had also sine and cosine, we had sine and cosine. So the boundary conditions knock down some, but you still have those interdependencies between those parameters and whatever else you have in the other equations. All these are interrelated. So we have to go back to these to get those interrelationships. Well, to do that, we usually reduce those equations a little bit. We manipulate them. First of all, we recognize that derivative with respect to the coordinate z, all of these will have that form of propagation, of wave propagation in the frequency range above cutoff, right? If we are above cutoff, we know that we have propagation. Below cutoff, we're not going to worry about it, okay? That's a different kind of analysis, which we are not going to bother with. We are interested in the waveguide when it propagates waves, because that's really the useful operating region. Typically, that's where we operate our guides. So the partial z is going to give you the J beta, right? Partial z is going to give you the J beta, plus or minus J beta, obviously. So all partial z's here can be replaced by plus or minus J beta, if you wish. If you were to consider only the positive going waves and add those later, which we typically do, just consider you have an infinite guide that doesn't reflect. We start with that, and we can always add that later on, right? Because the ratio between this and that is going to be a reflection coefficient depending on the termination at the load end. We've seen that in transmission lines. So having that in the background, I don't have to bother about this one for now. Maybe I can just work with that, and maybe a minus J beta will be adequate. We can worry about the plus J beta when we add this component later on. So this one here will give us a minus J beta. Here we'll get a minus J beta. Obviously E sub y. I need to write that down. This one H sub y, H sub x. In here, minus J beta, E sub x. Next thing, we rearrange those, and the whole point is I want to put them in terms of, I solve for E sub z, right? So I need to get it in terms of E sub z. As it turns later on, we can put it in terms of E sub z and H sub z. So I can rearrange those, and I'm not going to do that because it's a couple of lines here, but you know, I scribbled down the steps. I'm just going to write it down. I'm not going to do the deviation for this part here. It's straightforward. You can rewrite those as H sub x is equal to H sub y is equal to, let me leave some space here in some decimal case. E sub x is equal to E sub y is equal to. And all of these will be in terms of partial E sub z, partial x, and a partial E sub z partial y. The coefficients here, I'm going to use this one here, it's going to be better. Partial E sub z, wait a minute. That's an intermediate step. I need the final step. The final step is right here. That's why they want to go through the steps. There are about 4 or 5 lines in between. It's going to be E sub x is equal to partial E sub z partial x and partial H sub z partial y. I got the final step here. That's H sub z. Final step. And the this was the E sub x. I'm sorry. No, it's H sub E sub z partial y, H sub x. There we go. I had it backwards. That's the H sub x. Partial E sub z partial y, partial x, H sub z partial x. Okay, the H sub y will have a partial E sub z partial x and have a partial h sub z partial y. And this one, e sub x, will have partial e sub z partial x and partial h sub z partial the ex, h sub z partial y. And this one will have partial e sub z partial y and partial h sub z partial x. There will be coefficients here in all of these. And we'll say a plus in all of these. We can manipulate those and get them in that format, okay? I can write you some of those coefficients so you can see it. This one here is j omega epsilon partial h times j omega epsilon divided by k sub c squared. I'm going to tell you what k sub c squared in a minute. And this one here minus j beta over k sub c squared. The h sub y is minus j omega epsilon over k sub c squared. And this one here is minus j beta over k sub c squared. This one here is minus j beta over k sub c squared. And this one here is minus j omega mu over k c squared. And finally, this one here is minus j beta over kc squared and a plus j omega mu over kc squared. Kc squared is omega c squared mu epsilon. Right? Remember omega sub c, which is the cutoff frequency, the radian frequency. K is omega squared mu epsilon, so kc squared is omega squared mu epsilon. Kc squared is that term. It's obvious that if I have E sub z and H sub z, I can get all the other four. Right? It's obvious that all I need now, in addition to solving for E sub z, right, that we need to solve for H sub z, which is going to be done similarly. Applying the boundary conditions, you get your thing. So we needed that too. So we started with this and we have it. So that was supposed to be next. Once we do that, so that was step one. That's step two. And this here will be step three. As you can see, you will have your final solution in terms of EZ plus and EZ minus and HZ plus and HZ minus. This one here supposedly will have an HZ plus and HZ minus. So all your solutions here will be in terms of E sub z plus and E sub z minus, H sub z plus and H sub z minus. And like we said, these are secondary because these come from the termination at the end, right? And E sub z plus and H sub z plus are going to be these will be determined by the source, how much signal the source is putting through, and this will be like the how much is the reflection from the load, right? Now, it's going to get very involved, lots of details, and the board is going to be filled with equations, and we're going to lose our way, right? So, as it turned out, that the people before us said, why don't we break this problem into two separate problems, and we solve each one alone, and then we claim that the final solution is the superposition of the two. Said if we are dealing with E sub z and H sub z, why don't we divide the story into two different stories? One story with E sub z alone, another story with H sub z alone. So we're going to break the solution now into two separate solutions, or two separate cases. Case 1, we say E sub z exists and H sub z is 0. Case 2, E sub z is 0 and H sub z exists. The general case will be the sum, right? If neither is 0, you simply sum the two solutions. That's what we do when you have more than one source in linear systems. You consider the effect of each source alone, and you superimpose the solutions as a result. Obviously, if you put E sub z is equal to 0 and H sub z is equal to 0 simultaneously, what do we get? Look at this.
0.
0. Right? So the case of both equal to 0 will result in 0 cross-sectional fields as well. Ex, Ey, Hx, Hy will be all zeros. So you can't have zeros for both Ex and H. So we'll say here, E sub z is equal to H sub z is equal to 0 will result in all fields equal to 0, no propagation. As turns out, that the case of all field is equal to 0, if this is all 0, that would come from when m and n both are zeros, right? You will discover that that's the case of m and n being zeros. One of them is 0 is fine, right? But both of them are zeros because let me show you what the solution for H sub z looks like first. I guess you need to see that to appreciate that. If we do the H sub z and go through the boundary conditions, H sub z, here it is. This is for the special case of one of the modes. That's not the general case. Okay, well, I don't have it. I thought I had it, but it doesn't look like I have it. Okay. Well, you will see that later. That's a special case. All right. So, anyway, we'll get back to that discussion later. The case when you have H sub z is equal to 0, that means your H field is only Hx and Hy. When you look here, your H will be Hx Ax plus Hy Ay. So the field is in the cross section only. There's no longitudinal field. Field in cross-section only was H sub z is 0. We'll call this case here transverse magnetic. Transverse magnetic. This case here, where E sub z is 0, we can likewise call it TE, and it will be transverse electric. So we're breaking the problem into two different sets of solutions. One of them is transverse electric, and the other one is transverse magnetic. And the general case would be neither. It's just simply the superposition of the two. So let's start with the TE modes, or the TE solution. The TE solution, that means E sub z is 0, right? E sub z is 0, E sub z is 0, E sub z is 0. We have simply our expressions for the magnetic field. Let me look at this expression again. Now this has a boundary conditions on all. I think this is the correct expression here. Okay, I think this is the correct expression for H sub z. Let me write you this expression here, and if it turns out to be the wrong expression, I'm going to let you know later. But I think it is the right expression, because it has cosine m pi x over a, cosine m pi y over b, hz plus e to the minus j beta z plus hz minus e to the plus j beta, the cross-sectional term and the z term. I think this is the right expression. It's not a special case. Yeah, I think so. Obviously, this is going to be m and n. This is going to be m and n. M and n. The beta is m and n. And the beta here is m and n. All of these will get subscripts m and n. And the overall H sub z will be the superposition of all possible m's and n's. So we'll go back here now, and we'll say for the TE modes, we erase this one here, and this, and this, and that, and then we'll just substitute this in here. What do we get? You differentiate that with respect to the x, you get m pi over a, and with a minus sign, minus sign here, so it'll give you a j beta over kc squared, and the derivative gives you another m pi over a, and then you have sine. I'm going to write simply sine the x part, cosine the y part, and then the square bracket. So I'm going to erase those so I can write them here. Sine m pi x over a, cosine n pi y over b, and the square bracket for the z. This one here will be differentiated with respect to the y, so I get a plus j beta over kc squared. I have n pi over b. I have cosine m pi x over a, sine n pi y over b, and the square bracket for the z. this one here is going to be a minus j omega mu over kc squared. So it's going to give me a j omega mu over kc squared. I'm going to differentiate with respect to the y and get n pi over b cosine m pi x over a sine m pi y over b. Square bracket. And finally this one here I get minus j omega mu over kc squared, and I get differentiated with respect to x, I get m pi over a, I get sine m pi x over a cosine m pi y over b times the square bracket. Here's the solution now for the TE modes, the HZ and all the other H's and E's, right? HZ is right there, and the HX, HY, EX, EY as well. You notice right away the similarity between this one and that one, except for different coefficient. So HX and EY are similar to each other. And if I divide them by each other, let's write down EX over HY. What do I get? All that cancels out. It's EY over HX, I'm sorry. EY over HX. I get J omega mu, I'm sorry, right here. Minus J omega mu, m pi over a cancels out. Minus J omega mu divided by minus J beta. I get plus minus omega mu over beta. Let's divide EX over HY. What do we get? We divide this by that and get the same exact thing, omega mu over beta.
Sorry, what did you say was in the brackets there?
The Z coefficient.
Okay. For all of them?
For all of them is the same, because nothing is going to change. You are differentiating only with respect to x and y,
Okay.
right? So the Z term stays as it is. You guys remember what's the ratio between E over H? In plane wave propagation. The intrinsic impedance of the medium, right? You divide the electric field by the magnetic field, you get the intrinsic medium impedance of the medium. Likewise, in transmission lines, like dividing voltage over current, you get the impedance of the wave, right? The wave impedance itself. This is intrinsic impedance, but not only the media now, that's in the guide, right? The guide has its influence. It doesn't give you the pure intrinsic impedance because that's beta inside the guide, remember? And that's beta inside the guide. And has an M and N in it, has an M and N, right? If you go beta in the guide, M and N. If you go with the intrinsic impedance of the media, eta of mu and epsilon is simply omega mu over beta, which is the square root of omega squared mu epsilon, gives you square root of mu over epsilon, right? And that's the square root of mu naught over epsilon naught, square root of mu relative over epsilon relative, and that was 377 ohms. Remember that? Modified by the relative permeability and relative permittivity of the media. That is your unguided value. U for unguided. Okay? Well, this one here, we'll call it eta in the guide for the mode M and N. I have to add further that this is only for the TE mode. Because we're working TE modes now, right? The TE solution. If you take the ratio between these two, eta guide for the TE over eta unguided is going to be, if you take the ratio here, it's going to be beta over beta guide, which is actually lambda guide over lambda. We did that before, and that turns out to be 1 over the square root of 1 minus FC over F squared. M and N. I'm dropping the M and N. M and N is always there. M and N. So your characteristic impedance, your intrinsic impedance is going to do the same thing versus frequency. If that's your F sub C, again, let's say that's a ratio here of eta unguided, your eta will go to infinity and will asymptotically approach. That's your eta guide, M and N TE. It's going to do the same thing. Your characteristic impedance or intrinsic impedance of the media in the guide will be higher than that of the unguided one. Same exact relationship. Why is this negative? Do we have a negative impedance? It's not imagining, it's just negative. How about if I take the minus sign from here and put it here? Would that be okay? Well, the thing is, you have to look at your wave in the direction of propagation, right? To form a right-hand system, right? E cross H gives you propagation that way, and that's how you see the impedance, right? So if you look at your right-hand system, I can move those to the right. That was HX, HY, or yeah, EX, EY. Was that the correct order? Sorry, can spare a space here. That's XY, and that's Z, right? So if your wave is propagating this way, and that is, let's start with the one that has a positive sign, the EX. EX, and that's your HY, correct? That produces the right-hand system and everything is fine. But if you want to talk about the other combination which gave us a negative sign, that was EY and HX. So that's your EY here. Let me do that in a different color. EY. To get a right-hand system with that, you need to talk about negative HX to get the right-hand system. So the ratio between EY and minus HX still give you the same impedance. Let me do that like that. So that was the minus sign that I had before, and I simply crossed it with blue. So this way you can see the change that we did. We took the minus sign, put it with the H, to produce a right-hand system, and we get what makes sense. The ratio again between E and H is your intrinsic impedance. And your intrinsic impedance does that. Obviously, if you want to worry about the Poynting vector, the Poynting vector is what? Is E cross H, right? The Poynting vector is E cross H. You have two components to that. You have the EX cross HY and the EY cross HX. Right? Since we need to worry about negative HX, so I'm going to put a negative sign to all that, because that's the one really that I should be working with. So if you do a cross product between these two, you get the Poynting vector of xy, and you cross these for each other, you get another Poynting vector between, let me write, ex hy, and Poynting vector between ey and hx, and obviously the two Poynting vectors are pushing the power along the waveguide.